This week we start with section 1.4. In this section we collect some consequences of the completeness of the real numbers. This notion of completeness refers to the fact that the real numbers, the way that we've constructed them, so this extension of the rational numbers that we presented not long ago actually allows us to say that this new number system, so this new set of numbers that extends the rational numbers, so it includes more elements in the rational numbers, but preserves all the structure of the rational sitting inside this new set called the real numbers, has no holes. So this is very important. For instance, when we try to define a number whose squared is equal to 2, there will be 1. I mean, you know that there are many elements. I mean, you can, if you take the squares of rational numbers, you may get as close as you want to 2, but never be equal to 2. I mean, there was the starting point of the discussion surrounding the necessity to build a new, I mean, a bigger set of numbers, so a bigger, so a larger set that would encompass the rationals. That will allow us to guarantee that when we have this kind of property where you can approach a certain number by making some operations with the rational numbers, then there will be a limiting number that would actually satisfy this property that we're approximating. And so that means that these numbers are complete in the sense that there are no holes in them. So whenever you're reaching something, you're approaching something, such as the case of the square root of 2, when you try to define it, then you will not find yourself unable to complete the task and take things to the limit. And so that's the concept of completeness. More rigorously, this is something we're not going to do now, but in metric spaces, you speak about completeness in the sense if you have what's called, I mean, I don't know if you remember this from Calc 1 or not, or Calc 2, depending on where you took it, or when you took it also, but the Cauchy sequences is a notion that sometimes is introduced there as early as somewhere in the calculus sequence. But whenever you have a sequence with a property that sequence exn, such as for very large n and m, xn minus xm is very, very close to 0, which means that the elements in the sequence are approaching each other, then that sequence must have a limit. That's actually the notion of completeness that we deal with when working on metric spaces. So this is the same thing as here. So this notion of completeness that we have now for the real numbers, which is manifested in, I mean, this is realized in the fact that realized by the fact that we have a supremum for every bounded set. It allows us to prove also that this notion of completeness, this rigorous notion of completeness for metric spaces, actually holds for the real number system. And so the completeness, so the least upper bound property that we know holds for the real numbers least upper bound property. What is this? So A subset of R is bounded. So we have a bounded above. So a set, we have a set that is bounded above has a least upper bound. Set A, again, subset of the real numbers. This is not true for if you place everything in Q. So this least upper bound property is true in R. So the statement here is that every bounded set from above, subset of the real numbers, has the least upper bound. So anytime you have a set, subset of the real numbers, and has an upper bound, then it has a least upper bound. That's the consequence. And completeness is a statement about, say, sequences in this case. So if you have xn, so a sequence, so this is actually, again, every time you have a sequence, such that xn minus xm goes to 0, as n m go to infinity, is convergent. So both things are actually the same here in R. Completeness and having the least upper bound property are the same thing. So if you have that whenever you have Cauchy sequences, so for every Cauchy sequence is convergent, that implies that any bounded set from above will have the least upper bound as a primum, and vice versa. If every bounded set of the real numbers has the least upper bound, then every Cauchy sequence will be convergent. And here, this image that we have on the right, to complete this, every time we have a Cauchy sequence, that means that we have a set of a sequence of numbers. So x1, x2, to x3, x4, and then we start accumulating around something over here. So the problem in principle is that even though the points along the sequence are getting closer to each other, they may fail to land a certain value in the limit. Think of think about the numbers that are a sequence of numbers that are getting whose squares are getting very close to the 2. Then that sequence of numbers will certainly satisfy this property, that their difference is approaching 0 as n m go to infinity. On the other hand, if you place that, if you take a sequence of rational numbers and those rational numbers will not converge in Q, because if they would converge, then they will have to converge to square root of 2, which doesn't exist in Q. But if you place everything in R, and you take actually any sequence of numbers that are converting to the square root of 2, or such that their squares are getting closer and closer to 2, then there will be a limit. I mean, of course, the difference will be going to 0. So there will be a Cauchy sequence, but you're guaranteed then to find a limit. So they will converge. Okay, so again, going back to Q. In Q, you may define a sequence of numbers whose squares are approaching 2. And that means that their difference, the difference of the elements in this sequence is approaching 0. So the differences are approaching 0, while there's no limit to this sequence. The only possible candidate would be and is the square root 2, and that is when you embed everything into the real numbers. And of course there they have a limit, because that sequence is convergent, and it's by virtue of completeness. And the reason that there's a limit, again, and now you can see how this comes into play, the fact that we have a least upper bound, because as we've talked about before, when we said, oh, we're going to define the square root, and we're going to see very soon how to define the square root, that actually can actually be defined as the supremum of all the rational numbers whose squares is less than 2. So see, I mean, finding a limit and having a supremum can be related to each other. So that's where, I mean, that's basically where we're at. And this notion of completeness, again, I mean, it's more easily seen in the property from on the right. If you have a sequence of numbers whose elements are approaching each other as you go further along in n, so xn minus xm, or for n and m really large, there are differences going to 0, then you expect there to be a limit. And so, because if not, you have like this mental image that there must be a hole in the real numbers. There's no hole in the real numbers. That's the whole point of the construction. And the first theorem that makes this notion somewhat precise, which is not having a hole, is the theorem 14.1. Let me see. Which is what I mentioned before, is the nested interval property. What does it say? I mean that if we take a collection of intervals, closed intervals, that is very important. If not, the result is not true, as you'll see in one of the examples in the exercises for this section. If you have a nested sequence of closed intervals, meaning that each one of these closed intervals contains the next, then the intersection of all of these intervals is non-empty. Okay, so nest interval property for each and in n, so for each natural number assume we are given intervals in, closed intervals in, and these are all the real numbers that are between these two endpoints, including the endpoints. That's the notation for closed intervals. Okay, so we're including the endpoints and every number in between, an and bn. So we have a family of closed intervals. Now we have assumed that they're nested. Meaning that each one of these intervals contains the next in the family. So I sub n contains I sub n plus 1. Let me just rewrite this one here. Then, what is the conclusion here? The resulting nested sequence of closed intervals I sub 1 containing I sub 2 containing I sub 3, etc., I sub n, etc., has a non-empty intersection. To be more precise, this means that the intersection n equals 1 to infinity of the intervals I sub n is not the empty set. This is not the empty set. Okay. So the proof, of course, exploits the fact that we have the supremum property, the least upper bound property, okay, and so that's what so that's basically what we need to do now. So we need to apply the we need to consider each one of these numbers an, and we'll find that they have a supremum, and that element will lie between an for all for all n and bn for all n. And that's how we're going to proceed to produce this number. Okay, so we must find, the thing is we have to keep track of what we are asked to find. So for this intersection to be non-empty, we must be able to find one number that is inside each and every one of these INs. So we must find an x x a real number such that for all n in n, x belongs to I sub n. If you go back to the definition of the intersection of a family of sets, belonging to this intersection means that you belong to each one of these sets over here. So you belong to the intersection if you belong to all, meaning each and every one of these sets. So when we find an element x, of course x cannot depend on n. It's the same x for every interval in. So an x in R such that for all n in n, x belongs to the set I sub n. Okay, so what we'll see is the following. So we now need to, as I said, we'll produce a supremum for the n. So let's define, so to that n, consider the set A, which is equal to an for n in n, right? So the left endpoints of the sequence of intervals. So now, and we are gonna set, so consider the set that. And so we see that actually every Bn serves as an upper bound for A. So let's so in particular, if we take B1, an upper bound for A. This should be clear. In fact, any Bn will do. And the idea is that if there were an AL, say, it would be greater than B1, this would be less than BL, and that would mean that, since this is greater than A1, the interval, so if this would happen, the interval A1 comma B1 would be disjoint with the interval AL BL, and then that will clearly violate the fact that that these intervals are nested. So B1 has to be an upper bound. And then what can we say once we know that there's an upper bound for the set A? Then there exists a supremum sub A for A. We're going to denote this actually as S. And so we want to show that this is in every single, this S, in fact let's call it X because this is the number that we want to find. We want to find a number that belongs to all these intervals. Clearly, by definition, by definition, X is greater than or equal to every n. In this definition, well, for every n in n, X is less than or equal to a sub n. Why is that? Because being supremum means that you're least upper bound, and that also means that you're an upper bound. So for every x and for every n, we have that a sub n is less than or equal to x. And that's just because, again, x is an upper bound. X is a least upper bound, and in particular, an upper bound. Okay? For the n system. As I said, this is the least upper bound, meaning it's an upper bound. Now, we also want to show that x is less than or equal to the bn's. For every n in n, bn is an upper bound for a. Why? We can just reason as before. If bn would be smaller than some al, then the interval an bn would be disjoint with the interval al comma bl. And then, well, in that case, the sequence of intervals will not be nested. Right? So the bn, any bn is an upper bound for the set A of ans, of all the ans. Since x is the least upper bound, for A, this means, so this implies that for all n in n, for every n in n, x is less than or equal to bn. Remember, bn is an upper bound of f for A for every single n. And any upper bound bounds the least upper bound from above. So that means that bn is less than no, Bn is greater than or equal to x. So putting this fact and this fact together, so therefore x belongs to In. X is in between An and Bn, right? So it satisfies these two inequalities for every n in n. By definition of In, so it's a closed interval, all those numbers whose values are greater than or equal to An and less than or equal to Bn. So by that definition, we know that the element x belongs to In. And so that means that this is true for every n. For every n. And since this is true for every n, we have found an element here that is in all the INs, meaning that it is also in the intersection. Okay, so since x belongs to the intersection, the intersection is not empty. It is non-empty. Which is what we wanted to prove. Okay, so we're done for now. This is it. So this is what this is the nested interval property, and now we know how this is a consequence of the supremum property, or the least upper bound property, which, as I discussed at the beginning, is the same thing as being complete. I mean, as R being complete. R satisfying the least upper bound property is the same as saying that R is a complete metric space with a metric. Well, we haven't actually defined a metric yet, but that's up for another discussion. We'll talk about that later on, if we have the time. Okay, but this is a very important consequence of the supremum, having a supremum, and then we'll see a few more. One that maybe you have anticipated for a long time is the so-called Archimedean property that you were asked to use in a previous work group session, and now we'll know why that is true. Just to give you a rough idea, the idea is that if you assume there is a number x such that n is less than that x for every n in n, that means that a set of natural numbers will be bounded. And since it's bounded, you would have a supremum. And analyzing what this means, you get a contradiction. Okay, so and that's what we'll see. We'll see next time. In the next video.